Welcome to lecture 67. So, in the previous lecture we just finished the satellite movement and about an oblate spheroid, and then we looked into how the sun synchronous orbit can be generated. Okay. Now, we look the perturbation on the satellite due to the third body. So, here in this case we can do a general treatment for this particular topic, but it is a very long, and this lecture is going to be the last lecture on the general orbit perturbation theory. So, in very brief I will discuss about the movement of moon around the earth and getting perturbed by the sun. So, this is the topic and I will discuss it briefly, so that today we finish this particular topic and then we get into the orbit determination problem. Say the earth is located here. So, this is your earth and moon is here and the sun is located here. This angle we write as phi, this angle we will indicate by psi prime and this angle will indicate by psi. Okay. So, this is not necessarily y. What I have shown here, this is just the psi and psi prime, it is a longitude of the moon and sun. So, under what assumption we are trying to work with? Moon is in ecliptic orbit, that means if this is sun and around the sun the earth is moving. So, this plane we have called as the ecliptic plane. And earlier I have shown that so if this is earth and earth equator is, and if this is the ecliptic plane. So, here the earth is there and this is the ecliptic plane which is shown here. So, equator of the earth will be inclined like this at 23.5 degree and moon's orbit it is around 5 degree inclined with the plane of ecliptic. So, moon's orbit will be somewhere say at 5 degree like this. So, with the plane of ecliptic, moon's inclination is not much. So, if we simplify the problem, so in that case we can indicate that their longitude it is a psi and psi dot. The in a general problem, say in the case of if this is the satellite, this is capital omega and we know this angle is u, which is omega plus theta. So, capital omega plus u, this is written as the longitude L. But if this angle of inclination is large, then it is not valid, because capital omega is in a different plane and u is in a different plane. So, it is not valid, but if the angle is small, I is a small. So, for a small I, we can write longitude equal to capital omega plus u. So, we assume that moon is in the ecliptic orbit and then we also assume earth is in circular orbit. So, earth is in circular orbit. So, this implies that the if looked from the earth, sun will appear to move in a circular orbit. Okay. So, this implies sun will appear to move around earth in circular orbit. And the third assumption we make, moon acts like like a point mass. See here, the sun is far away from the earth. Okay. If this is earth and sun is at a large distance, but still the oblate shape of the earth causes a precession motion of the axis of spin. As we know in the beginning of this course, I have discussed this part, that the earth axis it moves in a circle. Okay. So, this is the spin axis of the earth. So, it will move in a circle, and right now it is a pointing toward the Polaris, what we call as the pole star. In Hindi we call it the Dhruv Tara. Okay. So, right now the spin axis is a pointing toward the pole star, but it will not be so all the time. Another 5,000 years, this pole star, the Dhruv Tara, will no longer be the Polaris for the earth. And in around 25,800 years, or nearly 26,000 years, this earth spin axis goes once in the moves in a circle. Okay. So, this motion we call as the precession motion, and beside this we have also the nutation motion of the spin axis of the earth. This is called the nutation motion. So, it keeps bobbling. Okay. It will keep bobbling here it will keep, it will rotate like this, and also it will keep bobbling about this. Okay. So, this is called the nutation motion. So, this happens because of this sun, and it can be computed also. So, if you look one problem you will find in if you have done mechanics course, then you will see in the Weir Johnston book on the mechanics that there is a problem related to the earth, the inertia of the earth is given. So, this problem is related to the satellite attitude dynamics. So, then you have to find the period of what will be the period of precession given the moment of inertia of the earth and distance of the sun, and all these things are available. So, based on that the year in how many years it will complete one precession. So, that has to be computed, the period of precession. So, that turns out to be around 26,000 years, 25,800 nearly. So, here we then define psi equal to capital omega plus small omega plus theta, and psi prime equal to capital omega prime, small omega prime, theta prime. This is for the moon, longitude of moon, and this is for sun. And already we have looked into that r, the perturbation term due to the third body is given by g m prime by r prime, and this part we have okay, this part we have not done, okay, but still we do not have much time to carry out this work. But what we do here, that if we do the whole analysis, it will take little time. Okay, I will supply those materials to you. So, basically the perturbation due to the third body, it can be written as r by r prime to the power n p n cos phi minus r by r prime cos phi. And from where it is coming? So, I will supply you the lecture, the corresponding lecture for that. see exactly what we have done. If we go back and look here in this place. So, the moon is moving around the earth and this is getting perturbed by the sun. Okay. So, what will be the perturbation force acting on the moon? For this we have already done in the 3 body problem, we have written that particular equation. Okay. So, that particular equation can be utilized and the equation can be written. So, rather than discussing all those things because we do not have much time. So, we just concentrate on this. So, given that this equation is the perturbation potential can be expressed here in this format, which of course, I will supply you the respective material. Okay. We can expand this and write this as g m prime divided by r prime, and here this is your Legendre polynomial as we have worked earlier for the oblate spheroid. Okay. And this is summation 0 to infinity n equal to 0 to infinity, and here this is minus, this is a separate term. So, once we use this and expand it, so the first term you can see immediately p n p 0 cos phi, this term is equal to 1. So, therefore, this gets reduced to 1, n equal to 0, this will be, this part also be equal to 1. So, this way we can expand it and we can write this as r by r prime and cos phi p 1 cos phi r by r prime square p 2 cos phi and plus so on minus r by r prime cos phi. So, p 1 cos phi, this is equal to cos phi, and if we utilize this value. So, this term and this term will drop out, and then we are left with g m prime divided by r prime 1 plus r by r prime square p 2 cos phi. See, here we are taking them as the point mass. Okay. We are taking them as the point mass, and therefore, the perturbation due to the oblate shape and other things, they are not coming into picture. This is just because of the third body perturbation. Again, I am reminding, this is the third body perturbation, and from where we have got this equation, this I will supply later on while the course runs. Okay. And so on, all the terms can be written. This we can write as r by a square times a by r prime square times p 2 cos phi and plus like this. And p 2 cos phi, this term in the Legendre polynomial, this is equal to 1 by 4 plus 3 by 4 cos phi, and therefore, r gets reduced to minus g m prime by r prime, and see here, once we are writing here in this format. So, I have done nothing wrong here in that. A we have taken in the numerator denominator and separated out in these two terms. Cos 2 phi, this is cos 2 phi. R by r prime we have changed. So, r by a and plus higher order terms. A general treatment of this whatever we are doing, it is a part of a general treatment. So, actually I wanted to cover that general treatment, but already we have exceeded large number of lectures. So, I am skipping that part, and all those things I am going to supply separately as supplementary material, and this is a small portion I am just dealing with. Now, some of the results we are going to use here, which you will find in those supplementary materials provided. So, using those results, it can be written as 1 by 1 plus 4 a by now r prime will be equal to a prime. Here r prime, this is standing for sun, and if we are assuming the sun to be in circular orbit, okay, then this will be equal to a prime. So, this r prime we can replace in terms of a prime, and we can write as a prime square, okay. And then the other part remains r by a square. These are the minor manipulation which are done, 3 by 4 a by a prime square r by a square times cos 2 pi. So, we neglect the higher order terms. So, we terminate the higher order terms and simply write it as neglecting higher order terms. Now, 1 by 4 a by a prime square r by a can be expanded. All these materials you will find there and written here in this format, cos m. Actually, this can be taken also as the exercise problems. 1 plus 3 by 2 e square minus 2 e m cos m minus 1 by 2 e square cos 2 m. A square times cos 2 phi, this we can write as so r by a already we have expanded. So, this we delete here, and cos 2 phi we have to expand. So, phi we are writing as phi we have written somewhere, no, phi we have not still defined. Phi we have, phi is here. This is the angle between phi equal to psi minus psi prime. This angle we have defined. So, using this phi we can expand it. So, this phi is psi minus psi prime, and psi is how much? This is capital omega plus u, or capital omega u if we expand. So, this will be capital omega plus theta minus psi prime. Okay. So, this way we can write this cos 2 phi as, so cos 2 phi. So, this implies cos 2 phi will be equal to cos 2 theta plus 2 capital omega plus small omega minus psi prime. We write it this way, and then expand this term here. So, this will be cos 2 theta times cos 2 capital omega plus small omega minus psi prime minus sin 2 theta sin 2 capital omega small omega minus psi prime. Okay, so this expansion we retain this r by a here, because for this extension we do not have a space to write here. So, let us retain it here r by a square. So, only the cos 2 phi term we have expanded here in this place, and this the r by a term we are retaining it here. Okay, r by a cos theta. So, r by a relationship we are aware from our earlier derivation. So, this quantity will be equal to cos m plus 1 by 2. These are some of the expansions quite frequently used in celestial mechanics. You can use book by J. M. A. Danby on celestial mechanics, also by Smart and White. This book name is okay. Another book name I will give you shortly in the maybe in the next class. And obviously, Archie E. Roy. This is on the fundamentals of astrodynamics. All these materials I will provide the soft copy, handwritten soft copy. So, these are the expressions, and this we need to utilize in the this particular part. So, we can expand sin 2 theta and cos 2 theta here and replace this, and where theta is the true anomaly of the moon. So, if we do this, so r can be written as minus g m prime divided by a prime q a square 1 by 4 plus 3 by 8 e square. So, we need to insert all these values here in this and then expand. So, this can be written in this format and reorganized. Plus 15 by 8 cos 2 times capital omega small omega minus psi prime. Remember, this is an approximate analysis. Plus m This way we can expand it and reorganize to write here in this format. So, the first term here, this is a constant term, so this term gives rise to the secular perturbation. This is referring to secular perturbation. So, let us say that we write R 1 equal to minus G m prime divided by A prime q 1 by 4 plus 3 by 8 E square, and look into the corresponding how the periapsis is getting affected because of this. So, omega dot it can be written as 1 minus E square under root, this is from our Lagrange planetary equation dou r by dou E plus cot I divided by N A square 1 minus E square dou r by dou I. So, only we look into the effect of this particular term which is arising from this term multiplied by this particular term here. So, immediately we can see that because of this term this will be equal to 0, this particular part, this multiplied by dou r by dou I. So, this quantity is 0 because I is nowhere present here. So, we are left with just estimating N A square E dou r by dou E. So, we have to estimate this quantity. So, here we have replaced this by R 1. So, let us write here this as the R 1. Okay. We will write this as the R 1 because we are just looking effect of this term. We are not looking the effect of all the terms. We are separately looking the effect of different terms. So, this term will give rise to the secular perturbation, means it is a time dependent. Okay. Secular means time dependent. So, dou r 1 by dou E, this quantity from here we get as minus G m prime by A prime q A square 3 by 8 times 2 E, and this quantity, this is nothing but mu prime by A prime q, which is n prime square. So, n prime square A square, and this becomes 3 by 4 with minus sign E. So, dou r 1 by dou E is this quantity, where G m prime we are replacing by mu prime. So, mu prime by A prime cube, this equal to n prime square. And of course, 1 minus E square, then we have to evaluate this term. So, once we insert this, so we get minus minus sign gets plus. So, this gets 3 by 4 n prime square A square E 1 minus E square under root divided by n A square E. Then this term this drops out, A square term drops out, and we are left with 3 by 4 n prime square divided by n times 1 minus E square under root. So, omega dot is 3 by 4 n prime square divided by n times 1 minus E square. So, this gives you the rate at which the periapsis of the moon will move because of this term only, okay, not all the terms. So, if you try to match the result with the moon's perigee movement with rising because of this term, you won't be able to do, because the moon perigee movement it will involve all the terms, effect of all the terms, while here this is giving just because of this term which we call as the secular term, which is a constant term appearing here. Now, if we integrate it, so you will see that the T will manifest here in this place. Okay. So, but direct integration we do not do, we some of the terms where say the psi dot it is involved. So, there we do not do the direct integration. In this case we can do and write this as omega equal to omega 0 plus 3 by 4 n prime square divided by n 1 minus c square t. So, this is showing that this is changing with as the t is changing, and therefore, we call this as the secular perturbation. Okay. Similarly, the perturbation in the sigma we can work out 1 minus c square n a square e dou r by dou e plus 2 n a dou r by dou a. So, this is a Lagrange planetary equation and we replace this by 1 and look back into the equation. So, dou r 1 by dou e already we have calculated dou r 1 by dou e minus 3 by 4 n prime square minus 3 by 4 n prime square a square e and dou r 1 by dou a we have to compute. So, r 1 is given here. So, this quantity will be g m prime. So, g m prime already we are writing as this quantity we are writing as n prime square. So, n prime square 2 a, when once we differentiate with respect to a. So, this will give us 2 a. So, this gives us n prime square times 2 a and then multiplied by rest of the quantity in the bracket and then insert these two results into this equation. Okay. And that gives you d sigma by dt. If you work it out, the whole thing, this will result in minus n prime square. I am skipping some of the steps, 7 by 4 plus 3 by 4 e square. So, this is also you can see that this is just dependent on t and this will be a factor of this is also a secular term. So, this way the these terms are giving rise to the secular perturbation. Okay. So, a particular the celestial body movement it is a combination of the now you take the various terms, all the terms are available in that as we go back and look into this. So, though we have neglected many of the terms, but some of the terms which are visible here, here you can look into this particular part. So, all these terms are there. Okay. So, if we work for them, we will get perturbation due to various terms, okay. But out of that some are periodic, some will be the long periodic, some short periodic, secular terms and so on. So, the effect of them all can be combined and looked into the motion of the moon. Okay. So, we stop here and I will supply you all the related materials, because we require further at least some 7-8 hours to complete this part related to third body perturbation, which we do not have. So, we stop here and I will supply rest of the material in supplementary format. So, thank you very much.